Okay. So, good afternoon to all the students. Welcome to week 7 TA discussion for the course Electrical Machines 2. So, we will be discussing a few concepts on equivalent circuit of induction motor in detail. So, last week we discussed how to arrive at the equivalent circuit and how to combine the stator equivalent and rotor equivalent together so that we can get a combined equivalent circuit. Now, in this week, we will be discussing some more details about the equivalent circuit and how to arrive at the Thevenin's equivalent circuit, how to arrive at the Thevenin's equivalent of our equivalent circuit, and then we will proceed to understand how different losses can be modeled in a machine. So entire power flow diagram we'll be looking at, and what all powers involved in the machine, and what are all the losses that can be contributed, and what are the power we are left with at the end, because some power we will give to the machine, so entire power can't be translated into useful power for the load. So some losses will be there, core losses, copper losses, uh, those losses we will see now, and some of course mechanical losses will be there because of the movement, some because of the opposing forces there will be some movement losses. So this analysis we will look into in detail today, and then we will eventually solve some problems on the losses involved in the motor, so that you will thoroughly understand and relate the concept which we study to the problems which we are going to look at. So yeah, let's start with that introduction. Let's start discussing about the equivalent circuit first. First, what we will see is the three-phase induction motors equivalent circuit referred to stator. We already saw. So the same circuit we the point where we left the last week, we will start from that point only. We will take the equivalent circuit, and then we will proceed with the arriving at the Thevenin's equivalent, and for subsequently we will proceed for calculating current flowing in the circuit, what is the power involved in that circuit, and then we will see the voltages and some expressions like that. Okay. So yeah, let me do that. So again, we are starting with the three equivalent circuit of an induction motor referred to stator. So equivalent circuit of induction motor refer to stator. Why I have I'm stressing on refer to stator means the rotor side resistances and reactances are being referred to stator in this equivalent circuit by using the turns ratio. So to avoid that confusion, I am writing it here itself. So we are looking at a per phase equivalent circuit. So that's important actually. I will write per phase. So this same equivalent circuit will be similar to the rest of the two phases in a three-phase induction machine. So yeah, this is the input side, and there will be stator resistance that we call as R1, and stator reactance X1, and it is R1 and X1 as we know. So here we are giving supply. Let's say V the supply, or V1, and yeah, and here we will have magnetizing branch. You all know this is XM, and this one, now we are entering to the rotor side via the air gap. So similar to the stator side, rotor side will also have a reactance and a resistance. Okay, so this reactance is X2 if it is a rotor resistance. So rotor resistance refer to stator. So we call it as A square X2, where A is the turns ratio. And now resistance part we have R2 by S is the rotor side load resistance. That's what we saw last week. Now since it refers to stator, there will be a coefficient of A square here. So yeah, R1, X1 are the stator side parameters, and XM is also stator side magnetizing inductance, magnetizing reactance. And A square X2 is the rotor side resistance referred to, sorry, A square X2 is the rotor side reactance referred to stator side, and A square R2 by S is the rotor resistance referred to stator side. Now we know that in this circuit, R1 X1 and R2 X2 are very small when compared to XM. Usually XM reactance will be much more because the current required to magnetize the core will be of higher magnitude when compared to the other currents. So these magnitudes of R1 X1, R2 X2, these are very small when compared to our bigger XM. So I can just write R1 X1 R2 X2. These magnitudes are less compared to these XM. Now, at this, if we want to arrive at a Thevenin's, the point of analyzing this Thevenin's part is, see, we have some parameter in parallel, so it's difficult to do any kind of analysis when some parallel branches are involved. Current division and all will be difficult. So what we are trying to do is, at this point, I can mark it as AB. At the point, if we look from this side and we try to simplify this part into Thevenin's equivalent, then it will be easy. So that's the only point to go for this Thevenin analysis. So at AB, I want to look into the left side of the circuit, and if from here, if I'm looking, so I can see R1 X1 and a parallel XM branch. So I am now trying to replace this all parameters into a Thevenin's equivalent. So I have a V1. So when I look into this XM, I will have Thevenin's voltage. Thevenin's voltage will be there. That is voltage across this branch. What is the voltage across this branch? It should be V1 multiplied by this impedance divided by total impedance. So yeah, that will be the Thevenin's voltage. And next, the equivalent impedance. So this is R1 X1. So voltage we will short, and R1 X1 in series, and the series R1 X1 will be in parallel to XM. So there we will get the equivalent impedance. So I will just write it here. So yeah, this is VTH. One second. This is RTH and this is XTH. So yeah, this one we have replaced this part from AB. This is A and this is B. Now the rest part is same anyway. A square R2 by S, and here A square X2, and VTH, RTH and ZTH. So what are the values of these VTH and all? So I'll be writing those here. So Thevenin's voltage, as I said, voltage across the XM branch, that is VTH. So voltage division principle, V1 into JXM, the resistance across that branch, divided by total R1 plus JX1 plus XM. So this is the Thevenin's voltage. Now what is this Thevenin's impedance? ZTH is equals to RTH plus ZTH, RTH plus JXTH. Now yeah, this is the total impedance, but what exactly, if we want to find exactly what is RTH and what is XTH, then we don't. So it is the parallel R1 plus JX1 in parallel with the JXM. So R1 plus JX1 multiplied by JXM divided by total. R1 plus J XM plus X1. So this is ZTH. If you solve it and separate the imaginary and real components, you will get what is the Thevenin's resistance and what is Thevenin's reactance. Now, since here R1 and X1 are already smaller, we know that if you connect two resistances in parallel, the equivalent resistance will be very close to the lower impedance only. So here R1 and X1 are very less in magnitude compared to your magnetizing reactance XM. So your equivalent impedance, if you try to calculate for the entire circuit, one second. So yeah, so if you try to calculate the equivalent impedance of the entire circuit, it will be same as the order of the low impedance. Yes, yeah. So your RTH and XTH will be as the same order of your R1 and X1. RTH and XTH will be of same order as of R1 and X1. Why? Why? Because we already discussed this R1 and X1 are very less magnitude compared to XM. So we have made a Thevenin's using that in Thevenin's you have done the equivalent impedance of two parallel branches. It is R1 plus JX1 and XM. Since R1 and X1 are having very low values, the equivalent impedance RTH and XTH will also be at the same order of your lower impedances. It is R1 and X1. So that's what this uh, equivalent circuit would look like. There is a Thevenin's voltage and there is a RTH and XTH, and that is in series with the resistances of rotor side. Now, yeah, this part we discussed. If this is stator and this is rotor, let's say this is stator side and this is rotor side, and to move from stator to rotor, we have to pass through the air gap, right? So this is stator and this is rotor, and this one we will call as air gap. So okay, now let's take this standard circuit of Thevenin's equivalent circuit and let's calculate what is the current flowing in this circuit, what are the powers involved in this circuit, and also what are the finally our aim is to get the torque developed in this machine. So we will see those uh, derivations now. Once again, for calculation purpose, I'm just redrawing our circuit. So this is VTH, this is RTH, XTH, and rotor side reactance and rotor side resistance, and RTH, XTH, A square X2, A square R2 by S, and this is stator side, this is air gap, and this is VTH. So okay, now we know last week we discussed the rotor current I2 is the rotor current I2, and if you refer it to the stator side, it is I2 dash. Now, since I2 dash is in now series, now there is no parallel branches involved. The same current is flowing in the entire circuit. This is I2 dash. Now, last week we solved the problems to find the rotor current. Now, the similar circuit we are doing it now for the Thevenin's circuit now. If you want to find the rotor current here, I2 dash. So what is this I2 dash here? Is the voltage divided by the entire impedance. Excuse me, entire impedance in the circuit. So the voltage is VTH, Thevenin's voltage, divided by entire impedance. It's a equivalent impedance of resistance part and also the reactance part. So I'm taking the resultant. So it will be here a resistance square plus it will be here the reactance square. So what are all the resistance in the circuit first? That is RTH and this A square R2 by S. So RTH. Now A square R2 I can term it as R2 dash, same like current. So it is referred to stator, and A square X2 I can write it as X2 dash. So if I use that representation, R2 dash by S whole square, plus what are all the reactances here? XTH in the stator side and X2 dash in the rotor side. So XTH plus X2 dash whole square. Now this is another important formula to find the current flowing in the equivalent circuit. Now you know what are VTH, what is RTH, and what is XTH. VTH is nothing but the voltage across the magnetizing branch. That is V1 JXM by total reactance in the stator side circuit. and RTH and XTH you will get by solving the equivalent impedance RTH plus JXTH. That is JXM in parallel with R1 plus JXM. Okay. So yeah, now we got the rotor current expression. Now, if you observe this expression carefully, you have a slip parameter here. Now, slip is a variable. Now, depending upon your speed and all, your slip, depending on the slip, you will have different speeds of your rotor, and this slip value varies between 0 to 1. Now, as the slip varies from 0 to 1, your rotor current will also vary because the expression of your rotor current depends on the slip. So, for different values of slip, at 0 slip and at 1, 1 means stand still, you know, and yeah, there is, 0 slip is there is no any uh, I mean, there is no any opposing forces in the circuit. That's ideal condition. That doesn't happen. That means your rotor is also rotating with the synchronous speed. No, so yeah. So 0 and 1 are the extreme conditions of your slip, and between this, your rotor current will vary as your slip varies. Now, okay, we have calculated the current in the circuit. Now, let's say I want to calculate the power. Now, for power, let's first look at the power flow diagram in a machine. So, let's look at what are all the basic losses that can come just by looking at the circuit, if you can see. So, power flow diagram. It's not an exact, not exact. So, because we are assuming some uh, assumptions. So, 1 second. Yeah. So if you see that, if you look at the circuit itself here, it's the equivalent circuit. Now if you see, there are resistance components here in the stator side and also in the rotor side. Within the stator side, we have RTH, that is stator resistance, and combined rotor circuit we have a resistance R2 dash by S, but that S is a varying quantity, but actual value physical resistance you have is R2 only. Whatever S is, because we have added the term R2 by S just to represent the variation of resistance with respect to slip. But while winding the machine, there will be a rotor resistance, that is physical value, that is R2. Okay, so we have a stator resistance RTH and the rotor resistance is R2. Now there will be power loss in these resistances whenever a current flows through them. We call them as a copper losses, or we also call them as a I square R losses. So whenever some current flows through these resistances, there will be some dissipating losses, that is I square R losses. And yeah, I'm just saying, excluding those losses, whatever power is left, you will get that power as a gross power, which is your useful for your mechanical movement of the machine. So we call that power as a gross mechanical power. Now that we are trying to represent it in a diagram that's called power flow diagram. Why I called it as not exact? Because I'm just taking the account of copper losses here. So apart from copper losses, sorry, apart from copper losses, we also have core losses, both in stator and rotor, and also some mechanical losses. We call them as friction, windage, and also bearing losses due to the movement of the machine. So we are neglecting all these losses. That's why it's not exact. Now we will also look at the exact power flow diagram later, but that will be a complex one. So before going to that, let's see what are the basic losses, so it will be easy for you to understand. Okay. Now I'm showing it in a diagram. Let's say, let's imagine this as a arrow. It's a path from A to B. While going from A to B, we are losing some power. So I will represent that as well, and we will arrive at the B. So the point A is starting point. Let's say it is the total input power I have given to my machine. Now, okay. Okay. Now, initially, if you see the circuit, after here I am giving the input power. So once the power enters the circuit, first it will encounter this resistance here that will contribute to some loss. So since the resistance is on the stator side, I will call this loss as a stator copper losses. Now there is some loss. I'm writing this arrow mark because some loss is happening here. So I will call it as stator copper losses. So that are equal to 3 I2 dash 3 I square R. 3 means it is total 3 for whole 3 phases, but this equivalent is per phase equivalent circuit. So I'm making the power flow for the entire 3 phase machine. So it's multiplied by 3 times. So 3 I2 dash square, and what is R here? RTH. That is the stator side copper losses. And now I proceed further. And now see, the stator side is done. Now I am entering into rotor side via air gap. Now at the air gap, okay, I have passed the air gap now. Sorry, I have passed the air gap and I encountered another resistance here. That is R2, R2. That is the physical resistance in the rotor side. Now there will be some more losses in this rotor circuit because of this resistance, current flowing through resistance. I will call this as a rotor copper losses, which is equals to 3 I2 dash square into R2. Now this in this between, I told you there is an air gap. So whatever power available at that air gap, we call it as air gap power. So PAG is nothing but our air gap power. Now I have multiplied, sorry, I have separated all the losses from the input power. So whatever power we are left at this end, that is the gross mechanical power available at the end that will be useful for my mechanical movement of my machine. So I will write this power as P gross mechanical power. Okay, sorry. Now this is what I am left with at the end of the circuit. So I have given some power. So there are some copper losses happened in the circuit, and I am left with uh, some power at the end. I am calling it as a gross mechanical. The reason why I am calling it as gross means gross always contributes to total mechanical power available. But I mean to say this is total electromagnetic gross electromagnetic torque available. Within that, there will be some losses in this as well. The entire gross mechanical is not utilized by the load, so there will be some mechanical losses in this mechanical power. Like I said, friction losses because of the friction between the machine, and also there will be some windage losses, and also there will be bearing movement losses. So all these small losses we contribute it as a mechanical losses, and we will subtract that mechanical losses from this gross mechanical to get the net mechanical. Whenever we call gross, it's a total, and whenever we call a net, that is actual useful. So that net mechanical power is what utilized entirely by the load. So there are no more losses in that. So moreover, I have not talked about core losses also. There will be some core losses like eddy current resistance losses as well. So if we have to include those two, and it will be even bigger power flow diagram that we will draw towards end of our discussion today only. Don't worry. And but before that, I just mentioning here the two basic losses here: copper losses in both stator and rotor. That's directly we can visualize from the equivalent circuit itself. That's the reason I have drawn it. Okay. Now, if you see the air gap power means once the stator the power passes through the stator, and it excludes the stator copper losses. Now my whatever power is available at air gap, we have to provide for the entire rotor circuit. So the total resistance in this rotor circuit is R2 by S, because there is a physical value of the resistance is there, that is rotor copper losses I square R R2, but my air gap power should supply to the entire rotor circuit. So if you see the entire rotor circuit, the resistances in the entire rotor circuit will be variable. It's not constant. That is R2 by S. So that's what my power air gap power will be. It's much more higher than the rotor copper losses. Now, if I write the uh, expression for my air gap power, one second. Okay. Air gap power, that is PAG. For three phases, it is 3 multiplied by, if you see the circuit, it is also I square R, I2 dash square, multiplied by the entire resistances present in the rest of the circuit. It's not the rotor circuit, it's entire circuit. So it is R2 by S. So 3 times I square R2 by S is the total air gap power. That is the total air gap power you need to supply to the all the resistors in the rest of the circuit. Okay, now from this air gap power, you will have to subtract the rotor copper losses, that is 3 I square R2. Then you will be left with the gross mechanical power. Now, I will do some small modifications here. There is slip this side. I will take slip this side and S into PAG. What you will be left with? 3 I2 dash square, I2 dash square into R2. But if you observe this expression, 3 I2 dash square R2 is nothing but the rotor copper losses. Now what you can write, rotor copper losses is equals to S into PAG. So that's what some relation you have derived from this air gap power expression. Okay, now you know what is air gap power and how much is rotor copper losses. And to calculate the gross mechanical, you have to subtract your whatever it is available in the air gap power. You have to subtract the rotor copper losses. So I will write that expression here. P gross mechanical is equals to air gap power minus rotor copper losses. Now you know PAG. Just now we derived rotor copper losses as a slip times of air gap power. Now if you take air gap power common, it will, you are left with this expression, which is a gross mechanical power. So this is a very important relation in induction machines, and based on this, many problems you will come across. So it's very simple relation and very useful relation to solve the problems. If you remember the simple relation which I am going to write now, you will be able to solve many problems in induction machine. Even at the gate level, you will get at least one or two problems based on this relation. It's just a very simple relation in induction machines, and it will be easy. So I'm just writing it here. That is, in a three-phase induction machine, if you take the ratio of all these, air gap power is to, one second, air gap power is to rotor copper losses is to, and last one is P gross. Yeah, P gross mechanical is equals to, in terms of air gap power only. All three we got in terms of air gap power. If air gap power, it's 1. Rotor copper losses is S into PAG. So the ratio will be S, and P gross mechanical will be 1 minus S times of PAG. So it will be 1 minus S. So this is the very important relation. You can just try to understand and remember. So P air gap is to P rotor rotor copper losses is to P gross mechanical is equals to 1 is to S is to 1 minus S, where S is called the slip of the machine. Now if you see, when if you keep S is equals to 1, like let's say S is equals to 1 here, your air gap power will be equal to rotor copper losses. So whatever air gap power you will provide, it's a standstill condition. There is no mechanical movement. That also you can infer from here. So if S is equals to 1, if you substitute S equals to 1 here, you will, the gross mechanical power is 0. There is no movement. We already discussed the s equals to 1 condition. It's a standstill. Your machine is not moving. So whatever air gap power you will provide, it will be entirely to deliver the total copper losses in the circuit. There is no mechanical movement. So there is no gross mechanical power. It will be zero. So that condition we already discussed is it's a standstill condition. So now we will see what exactly this gross mechanical power is. P gross mechanical is equals to P net mechanical plus, as I discussed, it will be some P mechanical losses. Now this net mechanical power is useful for the load. Now whatever only this mechanical power will be useful for the load, and whatever power left with is the frictional, like the mechanical losses that contributes to the mechanical losses, like frictional losses, windage losses, and also the bearing losses. Okay, now this gross is the total opposing power. You can also call this as total opposing power. What is this total opposing power is, whenever your machine is rotating, your machine will experience the opposing power, that is electromagnetic torque, which is opposing force, that is whenever it is moving, the total electromagnetic power, the total power will be utilized by your load, that is net mechanical power. And also there will be some frictional power, that is also opposing, friction, windage, all are this opposing to the movement of the machine. Now from this total opposing power, if I want to calculate the total opposing torque, now we have come to the torque discussion. Total opposing torque. So this is what we are called as mechanical gross torque. So this is gross mechanical power. So the same torque we will call as total mechanical torque, or we can just call gross mechanical torque. So what will be this equal to? Torque is equals to what? Power divided by speed, right? So here, what is the power? P gross mechanical divided by this. It will be in radians per second. Usually we calculate it. That's the SI units. So if your torque is in Newton meters and your power is in watts and the speed should be in radians per second, then only you will get a Newton meter torque. Now radians per second means 2 pi omega s. That's what you will write. 2 pi ms omega. So 2 pi. What is the speed of the motor here? That is nr. nr means mechanical speed in rps. So I will write the expression for nr here. nr is equals to 2fr by p. You know, this is the rotor frequency and the unit will be mechanical rps. So yeah, this is the T cross mechanical. Again, you have to keep in mind it's gross, it's not net. We will see later what is the useful power at the end. So that we usually call as a shaft torque. So whenever you are provided in the problems at a 10 kilowatt motor or at a 25 kilowatt induction machine, that number, what they give in the problem, that is the shaft, that is the total output power. So that is at the end of the diagram. So even after removing all core losses, copper losses, rotational losses, like rotational losses, these mechanical losses, the output power available at the shaft, the total useful power, that is called the net power or the shaft power. Then the torque similar to that power will be corresponding to that power will be we call the shaft torque, that is the output torque. Okay, so yeah, it is 2 pi nr. So this is another important formula. Now, okay. Yeah, again, this is all substitution and getting some other expression. If you see, now we have seen the one second. Now we have seen the expression for torque here. Now we will just do some small arrangements and we will arrive at some other formulas. It's all different relations, and if you are provided with some data, you will use that data to calculate the torque. If you are not provided with the data, you will modify it the expression and you will modify it in some other expression which you have the data for. So that's what we will see. Okay. Okay. Now we have seen the expression for electromagnetic torque, or we just call that as total opposing torque expression we saw. That is, this is TEM, electromagnetic torque. Same opposing torque. Don't confuse with these many expressions. I will just use the word electromagnetic torque. That is what we wrote there. P gross mechanical divided by 2 pi nr. And now gross mechanical divided by 2 pi nr. Now we know we can replace this P gross mechanical as what? If I want to write in terms of air gap power, P gross mechanical, here we have written it here, it is 1 minus S times air gap power. I have just replaced. So why I am saying all these formulas are, it's very simple. If you remember this, you will be able to solve many similar problems. See, if you are solving for torque and they haven't given you mechanical power, they have given you air gap power. So you can just use this formula instead of this formula. So if you know the relation, it will be easy to calculate. But if you remember, it will be very easy. So okay, now I have replaced this one with, and if you see 2 pi nr, you know the relation between nr and ns. Nr is equals to ns into 1 minus s, where ns is synchronous speed and s is slip. You know that, right? Last week also we solved a problem on this formula. Okay. Now I am replacing an nr with ns into 1 minus s. Now in the numerator and denominator, 1 minus s is common. Now another formula for the same torque, it's air gap power by 2 pi ns. It's gross mechanical by 2 pi nr, and it's same as air gap power by 2 pi ns. So you can use any formula you want to based on the data you have been provided with the in the data in your numerical. So TEM, it is electromagnetic torque at slip S is equals to PHE by 2 pi ns is equals to P gross mechanical by 2 pi nr. So this is another important torque relation. This is combined. So your air gap power depends on your torque here, because you see, whenever you take a machine, if the supply frequency is fixed, and if your number of poles of machine, they can't change. Once you get the supply and you make the design of a machine, the poles you can't change, and the construction you can't change, the supply frequency you can't change. So the synchronous speed will be fixed throughout. Your rotor speed will change based on the slip, but your synchronous speed won't change. This 2 pi ns is always constant. So if you see this here, 2 pi in 2 pi ns is equals to 2f by p. This is also mechanical rps, rotations per second. Now this one is a constant, right? Now what are the units of torque? Newton meter. And what are the units of power? I'm talking about this formula. And if you take this formula, this one is in Newton meter, and this power is in watts or kilowatts, whatever it is. And in the denominator, 2 pi ns is a constant. Even though it has some units, it is a constant. That's why usually what they will say, your air gap power and torque are equal. There is just a constant term multiplied with the power so that you can get the torque. So usually your air gap power is also expressed in torque as synchronous watts. It means your power is in watts and your torque is watts divided by synchronous speed. So usually people also use this term. So they say as P is equals to PAG and the units will be in synchronous watts. Here the power is not in watts. Here the power is in synchronous watts. So PAG is in watts. PAG by synchronous speed 2 pi ns. It's in synchronous watts. If we take this entire ratio as a single term, then it's just torque is nothing but power in synchronous watts. So that's, you don't find these kind of expression usually because it's a bit confusing. So what exactly is synchronous watts? But this again a useful thing to understand, because people sometimes maybe in numericals they can directly give you the air gap power, the air gap power of the machine is 1000 synchronous watts. Then you should not get confused by it. It's just they have divided this PAG divided by 2 pi synchronous speed, you get the synchronous watts, and you can take that number. Usually it won't be that 1000 or something, maybe 50, 60, 70 synchronous watts. So you can take that number directly as a electromagnetic torque or gross mechanical torque that is available. Okay. Now, yeah. So this is the units of this is synchronous watts, and the units of this will be, as I said, it will be Newton meters. Now, if you see, if you analyze the torque expression further, I'm writing the same expression. TEM is equals to what? Air gap power divided by 2 pi ms. So air gap power, we just saw the expression for it. It's 3 times 3I2 dash square multiplied by R2 by S divided by 2 pi ns. But from the Thevenin circuit, we just solved the expression for rotor's current I2 dash. Let's go back. So this one, we already solved the rotor current expression I2 dash. Let's substitute this I2 dash expression in our torque formula. Now this I2 dash square I am separately writing that side. Now what I will be left with, 3R2 dash by S divided by 2 pi ns into I2 dash square. I2 dash is VTH square divided by RTH plus R2 dash by S square plus XTH plus X2 dash by square S. Okay. Here VTH square will be there. In the denominator there is under root, so the square and under root gets cancelled, and you are left with RTH plus R2 dash by S square plus XTH plus X2 dash whole square. So I'm just rearranging it. I'm bringing the voltage this side and resistance part to the right side, so that you will have the entire resistance part to the right. So this will be very useful while solving the problems later. Using this torque expression, we will then see the exact power flow diagram. So we will also include core losses there, and we will see how this torque expression will change with respect to slip. And we will see an interesting curve now. Just after I will write this expression, we will see a very interesting torque slip curve and how we will get a maximum torque for different slip. That analysis we will see. So I'm just writing quickly. So 3 VTH square divided by 2 pi ns, and you are left with R2 dash pi s divided by. Okay. Okay. So this is the torque expression we have. This is usually most commonly used torque expression while solving the problems related to equivalent circuit. So in the question they will just give Thevenin's, or you can also calculate Thevenin's. They will give supply voltage and all. Equivalent circuit parameters RTH, R2, XTH, X2. XTH and RTH are R1, X1. You can calculate from that. So you have to calculate the torque. So you can do that as well. Now that's okay. That substitution calculation is okay. But the concept which we have to understand from this expression is, now if you see this expression, there is a slip value. Now let's say your equivalent circuit parameters are all done. So that you found all the parameters. They are constant. They are constant now. Your VTH, 2 pi, NS, R2 by S, all parameters are now constant. Now if I vary just my slip, your torque will be varied. Rest are all same, and you are varying your slip from 0 to 1, 0 to 1, and you will get different torques at different slips. Now I just for experiment purpose I will take S as the independent, and on the y-axis I will plot the torque. So from S to 0 I will just go 0.1, 0.2, like that. I will go till 1. So this 0.1 means 10% slip, 20%, 30% till 100% slip. So till 1, this is the standstill condition. I will get some torque. At 0, anyhow, you will get 0 torque. And like, because this R2 by S, it's 1 by 0 infinity. In this short total, you won't get any torque there. That's the starting position. And if you go on increasing the slip, and you will get some curve. Let's say this your points you got, and you are trying to plot. Don't think that at the maximum slip you will get a maximum current. That's not the condition. There is no, it's not a linear relationship between torque and slip. It's a non-linear curve. We will see that. Let's say this x-axis is slip, and y-axis is, as we discussed, the electromagnetic torque. We have started from here. Let's say this is 0, s is equals to 0, and let's say this s is equals to 1, and let's say this is the your maximum slip. Now the nature of your curve will be, as you vary your slip from 0 to 1, your slip is increasing from left to right, you will get something like this. Now, okay, I just will draw it like uh, the torque keeps on increasing, and at some point it will reach maximum, and again it starts to reduce, and it not exactly settles, but I just want to, yeah, let's say this is, it won't go to 0 here, because this is okay. S is equals to 1 means the starting condition, right? Standstill condition. There you will have some starting torque. That's what I want to show here. The slip at the starting is not 0. There will be some torque here. So you see here you got the maximum torque, and there will be some slip alpha corresponding to that maximum torque. So it says that if you operate your machine at this particular alpha, you will get the maximum torque. So that's the point, that's the slip at which maximum torque will occur. Now this is the starting slip, and this is your 0 slip, and okay, now at s is equals to 0 means it's not practically possible, right? That means you can say if NR is equals to ns into 1 minus s. If you keep s is equals to 0, your nr is equals to ns. Here the speed is ns, nr equal to ns. And if you keep s equals to 1, this means nr is equals to 0. That is starting condition. Here nr is equals to 0. Now if you see, the speed is increasing from right to left, this way. This way the speed is increasing, but this way your slip is increasing. So yeah, that's the relation you have. 1 minus s times of speed is nr. So your slip will be increasing in this way, and your speed will be decreasing in the same way. Okay, that's easy only because of slip and speed relation. Now, yeah, the point is this condition is starting condition, and this whatever torque available here, and this is you call starting torque TST, and this is TE max. Whenever if you come across a problem where you want to calculate the starting torque, you just substitute S is equals to 1, solved. You can get the starting torque. And to calculate the maximum torque, that's the issue. Maximum torque, you don't know at what slip it occurs. First, you have to find what is the slip at which the maximum torque occurs, and then you will substitute that slip in the torque equation. Then you will get the maximum torque. Okay. Now, let's say I want to find, but before going there, usually what manufacturers will say, if you, it's not exact, but their estimation, their assumption, whatever based on analysis they did, they say that if you operate your slip at around 10%, they say that if alpha is almost approximately equal to 0.1, that is 10% slip, that is good for the motor, because at that slip usually it gives maximum torque, they say, but it's not exactly, they can't say that exactly, but it's based on a study. But if you want to calculate, we can calculate. So like in mathematics you might have come across there is a curve, and if you want to find the maximum of that curve, what you will do, the most common and most standard technique is you will differentiate that curve, you will differentiate it, and you will equate to 0, and you will equate the expression to 0, so that you will get the independent variable there. If the logic behind this is, if you are differentiating, means you are calculating the slope of the curve. Slope, wherever the slope is 0, that means you have reached the peak of the point. So let's say this is the curve, sorry, let's say you have something, a curve like this. So this is y and this is x. This is at every point the slope will be this by this, y-axis by this point by this point, this point by this point. This is what you get the slope. So if you directly differentiate it, at every point here the slope is decreasing, here the slope is increasing, but at this point the slope is 0. There is no,
Sir,
yeah,
sir, we have to calculate alpha also, na?
yeah, you have to calculate alpha. What you have to do is, you have to equate this, you have to differentiate the torque and equate to 0 and find the alpha there. So that's what I'm coming
dt
there.
by ds equal to 0.
Yes, exactly,
Okay.
with respect to slip. So that's what I'm saying. So if you want to find the slope of this curve, you differentiate the curve dy by dx. So y is already a function of x. So equate to 0 and find the x at which this dy by dx is 0, so that you will get the point where you will have the maximum point or minimum point. So here you see this dt by ds, you do the differentiation of this expression and you will equate it to 0, uh, and you solve for the s in that expression, and you will get the slip at which the maximum torque occurs. But doing that is very complex. So this is already a second order equation. You have the quadratic expression in the denominator, and you will differentiate it, and you will, it's very tedious process. So even if you do that, you will get the answer. But there is another very simple process and very straightforward process, and using that you can easily get the slip value at which the maximum torque occurs. So the logic behind this is it's very simple. We already discussed that point. I will reiterate that point. Uh, we discussed that your torque is analogous to your air gap power, right? Because your air gap power divided by the constant will give you the torque. Now, if you want to have a maximum electromagnetic torque of TE, you should see the top expression. If you want to get this maximum, you want to have air gap power to be maximum. Then only you can guarantee your TEM is maximum, because anyhow this 2 pi ns is constant. Now, I want to have maximum air gap power delivered to the whatever circuit present. Now, this is a very standard theorem you have in networks. That is maximum power transfer theorem. That means you have some power at the input side. Now, I want total power available to be transferred to the load side. Now, what did the theorem say? The theorem says if you can able to make the load impedance equal to the impedance of the circuit, the load impedance is equal to source impedance, then you can able to transfer the entire maximum power to the load. So that's the standard maximum power transfer theorem. Now we will try to utilize the same theorem here as well. So what I am trying to do, I am trying to maximize this air gap power so that I will get the maximum torque. Now if you see, I'm just drawing the circuit. This is VTH and this is RTH, XTH, and this is air gap power, right? Now this I know R dash by S, and this is X2 dash. Now if you see the circuit, sorry. Now air gap power in this circuit, if you see, is dependent on your resistance. That is R2 dash by S, because air gap power is 3 I2 dash square R2 by S. And we also know that your torque and air gap power are same. They follow the synchronous watts. Now my torque will be maximum when this air gap power is maximum. Now my air gap power can be maximized. That means the maximum power I can able to flow through the R2 by S resistance by applying this maximum power transfer theorem. Now, now I'm trying to find at what slip my power will be maximum. So see here I am trying to deliver all my maximum power to the my R2 by S resistances. So if I can able to make this R2 by S equal to the rest of the impedance in the circuit. So what are all impedances is present? This. I want to make this impedance is equal to my load impedance so that I can guarantee this total my maximum power can be transferred. Now at this instant, whenever my load impedance, I am writing it alpha because that is the slip where my maximum torque will occur. Now R2 dash by alpha, if it is equal to the equivalent resistance, what is the equivalent resistance? RTH square plus XTH plus X2 dash whole square. See, whenever my load impedance is equals to rest of the impedance in the circuit, I can say that maximum power can be transferred. And the slip at this condition will be the slip which will give me the maximum power. Maximum power means maximum torque. So with this very simple concept, I found the value of the slip. If this you see the figure here, so at the slip where my maximum torque will occur. Simple from the simple relation I have found the value of alpha. I will write the value of alpha here. Slip at which TE max occurs. is equals to alpha. That is, go back to the alpha is equals to R2 dash divided by under root RTH square plus XTH plus X2. R2 dash, that's good. Now this is the slip at which my maximum torque will occur. Now you know only the slip value. Now what is the torque maximum value? Now use what is this TE max? Now you just have to substitute this value of alpha in this equation. This is TE, and you are trying to substitute S as this one in this equation. Now TE max is equals to, I won't be doing the entire derivation, but I will just write the initial steps so that it will be easy for you. R2 dash by S. I'm writing the expression. So first I will write the expression for TE. R2 dash by S divided by RTH plus R2 dash by S whole square plus XTH plus X2 dash whole square. Now TE max is equals to, this term remains same. There is no slip term in this first term. Now there will be, okay, R2 dash by S. See, S is equals to this means the slip. You have to substitute R2 dash divided by under root this one. So it's nothing but you can replace this R2 dash by alpha with this under root term. RTH square plus XTH plus X2 dash whole square. And here also there is another R2 dash by S term. And you can just replace XTH plus X2 dash whole square, another whole square, plus XTH plus X2 dash whole square. So yeah, you can expand this denominator a plus b whole square, and then in the right side also there are again XTH plus X2 dash whole square, and you take common and you take it will become 2 times entire formula, and I will just write, you can solve it later, and I am writing the final expression here. There will be a 2 term in the denominator. It will come to this side. 3 VTH squared by 4 pi ns. It will be 1 by RTH plus under root RTH square plus XTH plus X2 dash whole square. Now this is the maximum torque formula. After you know the slip at which the maximum torque occurs, you have just replaced this with the expression. So here you see there are Thevenin terms VTH, RTH, and XTH. You know this X1, R1, R2, X2 are very small compared to XM. So if at all in the problem they mentioned XM is very large compared to R1 X2 and R2 X2 R1 X1, and your VTH will become V1 and RTH will become R1 and XTH will become X1. So there is no XM term. XM is very large, means you can consider the VTH and RTH as V1, R1 and XT1 as XTH. Okay, now yeah, that's the total expression we are looking at here. Now you see an interesting thing here. That's what I was talking about earlier. In this maximum torque expression, it is independent of R2 dash, right? So your rotor resistance is not affecting the maximum torque. That's I mean, even if you change your rotor resistance, if at all there is a mechanism available at your rotor end where you can insert external resistances, keep on adding the external resistance. Like last week we have solved the problems of adding the external resistance. So if you keep on adding the external resistance at the rotor side, we have seen that in the last week the starting torque has improved. but your maximum torque do not change because it is independent of rotor resistance. Whatever might be the rotor resistance, you will have a fixed maximum torque uh, at the machine. So that we, if you want to visualize it, we already know the how the curve will look like, right? So this is TE, and let's say this is the TE max locus, and here is S equals to 0, and here S equals to 1, and here NR is equals to NS, and here NR is equals to 0. Okay, now let's say my typical curve is like this. Okay, this is the maximum torque I have occurred at the alpha. Now I have changed the rotor resistance. Now my R2 dash has become R2 dash plus R external. Do you think my curve changes? Do you think my maximum, the curve will change, uh, but your maximum torque won't change because maximum torque expression your R2 is it's not dependent. But what it is dependent on, your supply voltage, that is VTH square. If your XM is very large, you can say that VTH is equals to V1. So indirectly your supply voltage will affect the VTH. Let's say this is for a V1 supply, and now I have made it V1 by 2. Okay, I have half the supply. So why I'm saying all this, because you will get these kind of problems even in gate level. So they say that now the supply voltage has been halved. Now what will be the maximum torque? That cases will usually they will ask such problems. That's why I'm explaining. So you see here, if I substitute V1 by 2 here, that means there is a square term. So your torque will go down 4 times. And and will it affect TE max? Of course it affects. So your TE max, if your VTH goes half, and your TE max will be reduced 4 times. But changing that doesn't affect your slip at which your maximum torque occurs. See this expression careful. This is very interesting, and if you pay attention, it will be very interesting to see how the curve changes. Now I have changed only input voltage, that is V1. By changing V1, I am sure that my TE max will change because there is a VTH term in my expression. If you see the slip at which your maximum torque occurs, by changing V2H, your slip won't change. It is independent of voltage, supply voltage. Now, by this change, now I'm saying this change, V1 to V1 by 2, your maximum torque will definitely change. This is TE max by 4. Okay. But does my slip change at which my maximum occurs? It won't change. Your curve will just dip like that. That's very important. So this curve is for V1 by 2. Your torque will go down 4 times. Now, what will I do? I will insert an external resistance. Now I will do for this case. The interesting thing what happens if you add an external resistance is, you see the expression of T max. It is independent of R2. Even if you keep on adding the rotor resistances, the maximum torque will remain same. See, the maximum torque will be same here only. But you see the slip at which the maximum torque occurs. It is dependent on R2, right? Now, if you are keep on adding the resistances to the rotor circuit, your slip will keep on increasing. See, now let's say I'm quickly drawing the torque slip characteristics. This is equal to 0, and this is equals to 1, and this is T max, and I have a curve like this, and this is my alpha. Now this is for my R2 dash circuit. Now I am trying to draw the curve for R2 dash plus R external. So can someone tell how the curve would be? Will it get downwards, or it will move left, or it will move right? Any idea? So the nature of curve would be
Settle down.
no. If whatever you said, if it shift down means like this only left side. Shifting down will change the maximum torque. But I said changing resistance won't change the maximum torque because the expression is independent of R2. But what will change? The slip will change. Here you are adding the R external at the top right. You see adding the R external. Your slip at which the torque maximum will change, but the torque, the value of the torque remains same. So now, as your slip increase, there will be somewhere around this region. Your slip, the slip at which the maximum torque increased now, but the torque maximum is remain same. So curve will be something like this. Now you are having a torque. Sorry. Now you are having a maximum torque at this slip. Let's say this is alpha 2. Let's say this is alpha 1. And now you even increased. So let's say this is R2 dash plus R external. Now I have increased the R external further. What happens? It will again shift further. This is for R2 dash plus 2 times R external. Let's say I have increased this for 2 times. Now if you see one interesting thing we observed even in the last week, as you increase the external resistance in the rotor, your starting torque is getting improved. You can also see that from the curve here. This is the starting torque 1 for alpha 1. This is alpha 3, you say. Now, this is the alpha. I'm just. This is the starting torque. This is starting torque 1. And this is starting torque 2. And this is starting torque 3. Now, you can find some very interesting thing. I will keep on adding external resistance to my rotor circuit until I get maximum torque as my starting. So I have added till that point. So see, this is my starting torque. So TEM itself is my starting torque. But is it a good way? Is it a suggestible way to do it? No, because if you keep on adding rotor resistances, what do you how will your rotor copper losses will be? It's proportional. As you keep on increasing resistance, your losses will also increase. So it is not usually suggested to keep on adding these external resistances, but just for improving the starting torque, you can add some resistances and also some improvement in power factor or some improvement in your starting torque. You can add this. But the important thing what we have to see is if you keep on adding the resistances, your slip at which the maximum torque will change, but the value of maximum torque will remain same. But if you change your supply voltage, the slip at which the maximum torque occurs remains same, but your maximum torque value itself will change. So these two are very interesting phenomenon. So your problems will come like this. Now I have half the supply voltage, or sometimes I will say I have increased the rotor resistances. Now calculate the new maximum torque. Now calculate the new slip at which the torque occurs. So it should be very simple for you now, because if you understand this concept, okay, I know the torque speed curve. They said that this decrease the supply, and from the formula, if you see, if I decrease the supply, my torque value will decrease, but my slip won't change. And some also okay, if I given the condition where my rotor resistance is changed, my torque value won't change because my torque expression is independent of rotor resistance. But the slip at which the maximum torque will change because my slip will directly be affected by the rotor resistance, because the slip formula at which the maximum torque occurs is S is equals to R2 dash divided by RTH plus under root that one. So you will get a difference with that. Okay, so that's what. That's what you have to uh, observe here. So with that, this discussion on the equivalent circuit of a three-phase induction motor ends here. And as I said, now I will be writing. I will be discussing with you the power flow diagram of our induction machine in a very detailed way, because we have the last time the circuit which we saw was more like a approximate circuit, because we have neglected the core loss, we have neglected the mechanical losses as well. But let's include all those and let's see how our exact power flow diagram will look like. Now if you understand this exact one, solving the problems, we will be solving the problems also now. It will be very very simple. So let's draw exact power flow diagram. So starting I have mentioned it as not exact. Now we will be looking at all the exact things. So in exact means we have to consider the core loss also, right? There will be stator losses, and there will be core losses in the stator. Usually rotor core losses are usually we neglect, they are very very less, and rotor side copper losses will be there, and like I said, mechanical losses will also be there. So at the same way which we did for power flow of the approximate circuit, we will draw the exact circuit now. Stator side R1 X1, here I have the supply, and here I will have the core loss as well as magnetizing branch. So to model my core loss, I have introduced this resistance, and here again my rotor side will be there. This is R1 X1, and this is R2 dash X2 dash, sorry, X2 dash R2 dash by S. And this one, this is XM, and this one is R0. See, this R0 is core loss resistance. They say this one they use it to model the core losses in the stator. Now let's look at the power flow. Here I have input power. So yeah, like I said, first there will be stator, and this is air gap, and this is rotor. Now within stator we have another component now, that is core loss, that also we include in the exact power flow. Now first we will be coming across stator copper losses. Next we have come across this core loss component in the stator core loss, and then we enter the air gap.
Say stator or rotor core loss, na?
Stator core loss, stator side.
Both both will be stator side.
Sorry,
Both will be stator copper loss. Both is stator copper loss. I am saying.
copper, no, copper loss will be different. I will write now. I will write now. Once we enter into the rotor side, we will have the rotor copper losses. This is core loss in the stator. After crossing air gap, we will enter into the rotor side. Now in the rotor side, we will have, as you said, rotor.
Copper and core loss.
Yeah. Usually core loss in the rotor side are negligible. We don't even consider. But yeah, if you want to, you can include that. But I'm not including it because rotor copper losses are not considerable. And yeah, as I said, there will be mechanical losses now. See, last point we discussed till this point only. So here we say we will have the gross mechanical power, right? P gross mechanical. Now we also discussed this gross is a combination of net mechanical power that is available at the shaft end, that is output power, plus some mechanical losses. Now I will model that losses here. P mechanical losses. So I will also writing that friction losses, windage losses, and also bearing losses, some etc. So these are all the opposing forces which we will not be useful to the load, but we are losing power to this anyway. So these are very minute losses of friction and all. And now whatever we are left with is the net power that is useful for the load, net mechanical power. Now, this particular power which we are seeing here, net mechanical power, it is the final output power, or you can say the shaft power, or you can say useful power. Finally, it's also called as here we have written net mechanical power that is actually available at the output. Now, if you want to calculate any machine's efficiency, you need to see how much power I am able to use, how much power is useful to me, excluding all the losses. Now, if you find calculate efficiency is nothing but output power by input. Here, the output power is P net mechanical. You should not consider gross mechanical. That's wrong. Shaft power you have to calculate. What power is available at the shaft end divided by input power. So this will give you the efficiency of your machine. Okay, sorry. So now see, once you have enough power at the shaft end, now you will drop some load on it, and your motor will rotate the load. But one condition is where no load condition. So you have no load present in the circuit. Like, let's say you have connected a circuit, equivalent circuit, and in the machine you have connected the supply, and you didn't give any load. Now, what power will the circuit take? These are the powers you see here. See, there are many losses in the circuit, right? For all these losses, now your machine has to input has to supply. So under no load condition, whatever output you are getting at the motor end are nothing but the combination of all these losses. So when load is not there, whatever losses present in the circuit, so your supply has to supply to that losses. So that's another thing we usually say. No load power means the combination of all the losses. They usually term it as a uh, uh, no load losses, or you can say no load power is equals to stator losses plus rotor losses plus mechanical losses. So you can also term it like that. Or people usually what they will do, stator losses means sorry, yeah, stator losses you will have I square r copper losses, and so core losses and mechanical losses you have uh, the, uh, core losses that we have mentioned here, core loss component, and mechanical losses will be friction and windage losses. So these all three will contribute to the no load losses. Okay, okay. Now, okay, I think that's the exact power flow diagram, and this will be very useful for you to solve the problems. So, approximate is just consider copper losses, but now we have considered all the core losses and mechanical as well. This is the total power flow diagram, and now we will look into the problems. We will solve these problems, and I request everyone to solve with me. 1 second, I'll get my calculator. Okay, okay. So please take your pen and paper with you, and please solve with me. I think it should not be a problem for you now. We have discussed enough theory of the losses, and you have already saw the exact power flow diagram, and it should not be a problem for you. So please solve with me. So okay, the first problem. Let's see what data we have given. The bigger the question is, the easier the problem will be. That should you always consider, because the more data it is available in the question. Don't get worried about the size of the question. So usually we see a big questions and we will get worried. But the bigger the question, the easier the answer will be, because you are giving you have indirectly provided with lot of data. Okay. So the question here reads: consider a 10 kilowatt, three phase, 6 pole, 400 volts, 50 hertz star connected induction motor. Now, what is that power? 10 kilowatt. Is it input power? Is it air gap power? Is it gross mechanical power? Is it net mechanical power at the output? What power is this?
Input power.
No, they don't specify the input power like that. It's net mechanical power available at the output. So whenever a manufacturer or someone specifies the power on the nameplate details like this, the buyer or the consumer who buys the machine should know how much power is actually useful. So whatever power they give in the data is useful power only. If I'm going to buy a machine, I go and see the machine's nameplate details. There it was written as it's a 10 kilowatt machine. So it's like, okay, 10 kilowatt is my useful power. That's what I need. So here,
Maximum power.
no, 10 kilowatt is the useful power. That is the shaft
Okay.
power, or you can say the net mechanical power. Okay. Now 10 kilowatt, three phase, six pole machine is given for you. Okay. It's a 50 year supply. Now the stator resistance per phase is 1 ohm. At no load, it draws a line current of 10 amps. Okay. And an input power of 800 volts. Okay. No load, they have given us these conditions. At full load, it draws a line current of 20 amps and an input power of 12 kilowatt. Okay. So here itself you can see the difference. So if you see the no load power, it's only 800 watts. It's not even 1 kilowatt. But at full load, it's drawing 12 kilowatts. We just discussed in the no load, it has to supply for the losses only. That's what we have given here. Okay. Now friction and windage losses is 300 watts. Okay. That's all the mechanical losses we are given. And the rotor copper loss at no load is negligible. So here they are saying the rotor copper loss is negligible. Okay, we won't consider the rotor copper loss, and we have to estimate the stator core loss in watts. Okay, now let's note down the data once. It's 10 kilowatt, three phase, six pole, 50 hertz motor, and R1 is 1 ohm, and it draws a line current of 10 amps at no load. No load means I not. Uh, okay, 10 amps, and input power at no load 800 watts, and its full load is 20 amps, and input power at full load is equals to 12 kilowatt, and friction and windage mechanical losses 300 watts, rotor copper losses at no load is equals to 0, negligible. Okay. So this is all the data I have at my end. Now what is required? Stator core loss in watts. Okay. What is stator core loss? Like we have discussed in the power feedback.
800.
Sorry?
It's 800 watt
No, no, no.
stator core losses.
No. 800 is total input power, right? At no load. So this is the total input power at the no load is equals to 800 here at no load condition. So this no load power has to supply to stator copper loss, and it has to supply to stator core loss and rotor copper loss and mechanical losses. So all the losses it need to contribute, right? Now I will write at just the expression at no load P input no load is equals to P stator copper loss plus P stator core loss. That's what it was asked here. And rotor side we have rotor copper loss and P mechanical loss. So do you know the stator copper loss? Stator copper loss we uh,
3I 2 square RTH.
right, exactly. Now we are provided with stator copper. So here the equivalent circuit, see, R1 X1, like this it will be. Stator copper loss is this one. See, at no load condition, let's say there is a no load voltage and some no load current is flowing, and stator copper loss is this I square R losses, right? Now 3 I naught square, that is the no load current flowing in the circuit, I naught square R1, that is a so stator core loss, that's what we will find, plus rotor copper loss at no load. So what we said, rotor copper loss at no load is negligible, so we will neglect this. And what are the mechanical losses present in the no load? So this is 300. Whether it's no load or full load, mechanical losses will same. That's not any changing term. That's always constant. Now, for all these losses, you have to supply the input. Now, if you see the question, they have given this input power at no load is equals to 800. 800. Now, from this, you know all the parameters. You just have to calculate the stator core loss. Because I know no load current 800, 3 into what is the no load current drawn by the machine at no load condition?
10 ampere.
Yeah, 10 amps multiplied by R1, that is 1, plus P stator core loss plus 300. Okay, now from this you can easily calculate stator core loss is equals to 800 minus 300 minus 300. Okay, so much?
200.
Yeah, 200. Okay, okay. That's simple. That's a direct, straightforward question. We just have to equate all the losses to this one, and we will get the stator core loss. Now, the next question is air gap power at full load. Okay. Now, we have to find the air gap power at full load when we know the all the other losses. Now, let's get back to our standard power flow diagram. Now, from the diagram we can see there is an input power, and after subtracting stator copper loss and stator core loss, you will get the air gap power, right? Here it is the input power, and you subtract these two, and you will be left with air gap power. Now I will use that relation at full load. Now my P input at full load is equals to stator copper loss plus stator core loss plus air gap power. I hope everyone understood this step. From the power flow diagram only I did this. Air gap power is nothing but input power minus stator copper loss minus stator core loss. So using that I have found this, because the reason I took this relation because I have just calculated the stator core loss. I will be using that in here. Okay. Now, okay. What is the input power at full load? We are given that in the circuit. Sorry, data. The input power at the full load is,
12 kilowatt.
yes, that is 12 kilowatt is equals to how much is stator copper loss? We just calculated here. Stator copper loss is 3I square R, right? 300 How much is stator core loss? We just calculated 200 plus air gap power at full load. Now your air gap power at full load is equals to 12,000 minus 500. So how much it is? 11,500. Okay, or 11.5 kilowatt. That is your air gap power at the full load. It's nothing but the total input power minus stator losses, stator core loss and stator. Uh,
Excuse me, under full load that stator copper loss very, that current is very,
okay. Yeah. You are right. You are right. So here we have to the no load current. Sorry. We have to calculate this stator copper loss again. Thank you for pointing it out. So 3I square R1, where this I is full load current. Now to calculate the stator copper loss, it's 3 into, in the question it was given at full load my machine is drawing 20 amps from the circuit. 20 square multiplied by 1, and how much it is? 3, 1200. I'm sorry for that. So yeah, the new stated copper loss at full load are not 300, it's 1200. Now my air gap power at the full load is equals to 12,000 minus 1200 minus 200. So okay, it's 10600 watts, or it is 10.6 kilowatts. Yeah, thank you. So yeah, it's important to see it's a no load or full load condition. In no load condition, it was 10 amps, but definitely in full load condition, the machine will draw a bit higher current. So that was 20 amps. So we have to calculate the stator copper loss at the full load condition now, and then we will solve for the air gap part. Thank you. Now the next question is estimate the rotor copper losses at full load. Okay. Now rotor copper losses at full load. Okay. Now let's say you have entire power flow diagram, and now you know the air gap power, and you also know the output power. Now if I have my net mechanical power at the output and also the air gap, what are all the losses present in between? They are the rotor copper losses at the full load and also the mechanical losses. Now if you with this equation I can get the rotor copper losses. Let's go back to our diagram, and we were asked this rotor copper losses, and if you know this air gap power and net mechanical power available at the output, and you can get the rotor copper losses. So yeah, P air gap is equals to net mechanical plus this mechanical losses plus this rotor copper losses. So that's what you will get the equation. So from that you can easily get the rotor copper losses. Let's write that P air gap power is equals to at full load. That's important. So because at no load rotor copper losses are negligible. Rotor copper losses at full load plus P mechanical losses. This doesn't matter, no load or full load, it's same. Plus P net mechanical, or we can say P output power at full load. Now, what is the air gap power at full load? It is 10,600 watts. This is what required. P rotor copper losses at full load plus what are the mechanical losses are 300 plus what is the net mechanical output? It's the output power. It's a 10 kilowatt machine. So 10 kilowatt. Now from this, P rotor copper losses at full load is equals to 10,600 minus 10,000 minus 300. It's 300. Yeah, 10,600 minus 10,600 minus 300 is 300. 300 watts. So this is the rotor copper losses. It will occur at the full load condition. Okay. Now, yeah, it's again a simple power flow diagram relation only. If you are thorough with the power flow diagram using any relations, if you know that, if you know this, you subtract this, it will be very easy. Okay. Now we have to calculate the speed now. It's not into powers now. We have to calculate the speed. It's also not that difficult. Okay. And I use N because it's in RPM, FL. So we know N, capital N means RPM and small n means RPS. So this notations you have to keep in mind. So it will be easy for while solving the problems. So we are asked with the full load speed, and we know N is NR. Of course, it's NR. NR is equals to NS into 1 minus S, that we know. NS is synchronous speed in RPM and S is the slip of the machine. NS I can easily get because I have provided with the machine's parameters. 120 F by P will give the NS. Frequency I know, poles I know, I will get NS. But how to get the slip here? Getting the slip is the problem here. And if you can remember our power flow diagram and the relation uh, I have discussed in this session today, it will be very easy to get the slip value. Now let's get back to our relation which we have discussed today and highlighted.
Rotor copper losses from rotor copper losses are
Yeah,
different.
yeah, exactly. See, this rotor copper losses and air gap power, there is a relation. So rotor copper losses is nothing but S into PH, right? We have written here. Now if you know the rotor copper losses and air gap power, you know that we just calculated from the problems, and you can easily get the slip. So that's why I'm saying this relation is very important. We just remember this relation, you can solve many problems. It will be very useful for you. Okay. Uh, Now I'm saying that rotor copper losses is equals to S times PAG. That's the relation I know. Now, how much are the rotor copper? It is at full load, no? At full load, what are the rotor copper losses at full load? It is 300 slip times. What is the air gap power at full load? This is the problem. 10,600. Okay, 10,600. From this, you can easily calculate slip. How much is slip? 300 divided by 10,600. It's 0.0283. It means a 2.83% slip you are having for the machine. Okay, now it's simple. Now substitute this S here and calculate the NR. NR at full load is equals to NS into 1 minus H full load slip. Now NS is 120 into F by P. It's a 50 Hz machine and its poles are 6 pole machine. 6 into 1 minus 0.0283. So how much is this? It's 1000 into 0.9716. It's 1000, right? Yeah, 20. Yeah, okay. It's 971.698 units will be RPM. So it's if it is a RPS, if the problem is asked in RPS, mechanical RPS, it's just you don't take 120 F by P here. You take 2 F by P because it will be divided by 60 and RPM will be converted into RPS per second. Okay. Okay. Anyway, So yeah, this is the full load speed in RPM 971.698. Okay. Now we are asked to estimate gross mechanical torque developed at the full load. Okay. T gross mechanical developed at the full load. How much? We have discussed this exact formula today. If you go back to our discussion where we have derived the torque formula, where it is. Okay, CC. So this is the TEM. This is total opposing torque. I think we already wrote that. See, gross mechanical torque. Exactly what was asked in the question. It's P gross mechanical divided by 2 pi nr. So okay, I can write that P gross mechanical divided by 2 pi nr. Now, if you see the same expression, we have written this gross mechanical torque is equals to P gross mechanical 2 pi nr. It's also equals to air gap power by 2 pi ns. Because I know the air gap power at full load and I know 2 pi ns, it will be easy to calculate the gross mechanical torque. I will be using that relation. T gross mechanical is equals to P gross mechanical divided by 2 pi nr is equals to P air gap divided by 2 pi ns. So see, you can calculate the gross mechanical power from here. You subtract rotor copper loss from Ag, you can get gross mechanical power and divide by 2 pi nr. But that's long calculation. Now you already know air gap power. You know 2 pi ns. It's simple. You don't need to subtract anything from anything. Now T gross will be P air gap power divided by 2 pi ns. Here see the 2 pi ns, here ns is not in RPM, it's in PS, that we have to keep in mind. So how much is this is at full load, right? At full load, air gap power at full load, how much is air gap power? It's 10,600 divided by 2 pi into 2f by p, right? That's in RPS. 10,600 divided by 2 pi into 2 into 50 by 6. So calculate this and can someone confirm that with me how much they are getting? 4 pi into, okay. So I am getting a gross mechanical torque at full load is equals to 101.22 Newton meter. So if there is any calculation mistake or something, please tell me, or else this is what I am getting. 101 Newton.
Correct, sir.
Okay, thank you. Now we have to estimate the shaft torque. So we already talked about shaft torque. Shaft torque is something which is useful to the load. You can call it as shaft torque, or you can calculate the output torque, or you can also term it as a net available torque at the shaft end. Now see, shaft T shaft torque at full load is equals to what? It's a output torque. But in the problem, we are provided with the output power, right? P output is a 10 kilowatt motor. Now, torque is nothing but power of the machine divided by the speed of the machine, full load speed. Now, torque output is equals to power output divided by the 2 pi nr. Nr is the speed of the machine at the full load. Now, even we calculated nr also, that is at full load slip, we calculate the speed nr 971 something rpm. But here it is not in rpm. We can write it as P output divided by 2 pi nr by 60. So nr, you can write as nr by 60, where nr is in rpm. I write it like this because we calculated the nr value. Okay. Yeah, output is 10 kilowatt motor. 2 pi into nr is how much? 971.698. divided by 60. Okay, this also please calculate with me. 9 into 60, because if we do if I get some confirmation, then it will be good for validating. 2 pi into 971, so it's 98.274 meter meter. So I hope it's correct. Okay, if you observe this, gross mechanical torque, C, its total opposing torque is 100 or not 1 Newton meter, but available is a bit less than that. So you are losing some torque to the rotation towards this friction and bearing and also windage torques. So all these combined torques you are losing, and you are within this 101 Newton meter, only 98.274 is the useful torque. Okay. Okay. Finally, efficiency. It's very simple. Efficiency in percentage is equals to output power by input power into 100. So entirely at full load. See, output power at full load, input power at full load. So let's go back to question. So if you see, it is a 10 kilowatt motor, that's the output power, and input power at full load is 12 kilowatt. So you can see 2 kilowatt you are losing for all the losses in the machine. Anyway, that's what decides the efficiency. So output power is 10 kilowatt, input power is 12 kilowatt at full load condition, into 100 gives you the percentage. So how much is this? It is 83.33 percentage. So this is the efficiency. Yeah, it's a 83% efficiency. It's fine. You are losing only 2 kilowatt for all the losses in the machine, and you are left with 10 kilowatt useful power, shaft power. Fine. So yeah, so this is the last point I want to discuss with you all today. So let's have a quick summary of what we have discussed today. So we have moreover discussed our equivalent circuit in detail today. We started with our equivalent circuit which we developed in the last week. We took the circuit and we simplified the circuit much more simpler to avoid the parallel branch, and we replaced that with a Thevenin's equivalent, and we found out what will be the Thevenin's voltages and Thevenin's impedance parameters, and then we proceeded to finding the current, power and torque from that equivalent circuit. So current is a straightforward one, current flowing in the series circuit, voltage divided by that one, and then power flow diagram we saw, that is the approximate power flow diagram where only copper loss is considered, and based on that we developed very important relation for induction machines, that is air gap power is to rotor copper loss is to gross mechanical is in terms of slip. Is very important. You have to keep in mind in this one for induction machines. Okay, from that we came to torque discussion. Torque is equal to power by speed, and with that relations we developed expressions for electromagnetic torque, gross torque, net torque, and also we discussed some relations between air gap power and torque. And then we proceeded to maximum torque discussions. So we have arrived at the final torque expression, and we investigated when can I get the maximum torque from this torque expression. So then we saw a very nice understanding of torque slip characteristics, and we discussed how my torque slip varies whenever I change the supply voltage or whenever I change the rotor resistance, like that. And then finally we discussed the exact power flow diagram contributing to all the losses in my machine. Now based on that discussion we have started solving our problems, and we solved some few problems, very straightforward discussion. And yeah, please keep in mind what currents you are using. Is it no load or is it full load? There is a chance to do mistakes in that. Even I did a mistake in that today. So yeah, every parameter, every calculation you cross check twice, thrice, so that you. These are very simple problems. So if problems like this come to gate exam, you should not do any mistakes, because these are very scoring problems in induction machines. Okay, to cross check twice or twice and then do the calculations. So with that, we concluded our discussion on induction machines, equivalent circuit, losses, as well as uh, torque and power discussion. So if there are any questions, thank you and Kumar, thank you Anil. If you have any questions related to discussion, please do ask, and I will also discuss with you. And if I'm not able to answer, I will get back to you in the next week. Meanwhile, at any point of time, if you have any doubt, please raise in the discussion forum, and I will be there, and my fellow TS will be there to discuss the solutions with you. And yeah, if there are no doubts for today, I thank you all for patiently coming to the session and attending to the session, listening to me, and actively participating.
Thank you.
Thank you, Priya. Okay, we will meet the same time next week, 4 to 6 p.m. See you all then. Thank you.